So this is part 3 of section 4.4. We're looking at exponential and logarithmic equations, and we're going to look at this in a couple of applications. So we're going to use the tools that we saw in the first video and the second video to actually solve these application problems. The first question that we have is, if $20,000 is invested in an account earning 2.5% interest compounded continuously, determine how long it will take the money to grow to $45,000. Round your answer to the nearest year. That's going to be the whole place, like the ones place, the whole number. Use the model A equals PE to the RT. So in this problem, we're told that the principal is $20,000. And the rate we know is 0.025% times t, which is what we're looking for. And the question is, how long will it take to grow to $45,000? So that's our total amount accrued that we are looking for. So this is one of those examples where we have an exponential equation where there's only the exponent on one side. So what we're going to do is first we're going to divide by $20,000 on both sides. And we get 2.25 equals e to the 0.025t. So then we're going to take the log of both sides. Please note that since this involves e, we're going to take the natural log. So we're going to get the natural log of 2.25 equals the natural log of e to the 0.025t. By the power rule, that's going to give us the natural log of 2.25 equals 0.025t natural log of e. Natural log of e is just 1. So that's going to go away. To solve for t, we're going to divide both sides by 0.025. And when we do that, these will cancel, leaving us with t is equal to the natural log of 2.25 divided by 0.025. And we get 32.437. So rounded to the nearest year, that's going to be t equals 32 years. Now you can check your work. You could take this and plug it into the initial problem, do 20,000 times e to the 0.025 times 32. You might want to include some of that, and when you do that, you're going to get an answer that's really close to $45,000. For question 17, they give us a formula. It says the following formula relates the energy E in joules released by an earthquake of magnitude M. The equation is log of E equals 5.24 plus 1.44 m, where m, the magnitude, is greater than 5. It asks the question, what is the energy released by a magnitude 6 and a magnitude 7 earthquake? So we are actually answering two things right now. So what I'm going to do is for magnitude equals 6, I'm going to substitute that into the equation. And I'm going to then take this right-hand side of the equation and just solve that. I get 13.88. So log of E, the energy, not little e, which is a number. This is actually a variable that we're solving for, is equal to 13.88. To solve this, we're going to rewrite this in exponential form because I have log on one side. So the base here is 10, so essentially it's 10 to the 13.88 equals e. So when I solve that, I get that e is equal to 7.5, I'm going to round to the second decimal place, times 10 to the 13th power. So that is for the magnitude 6 earthquake. For the magnitude 7, we're going to do the same thing. M equals 7. Substitute that in. So we get log of E equals 5.24 plus 1.44 times 7. which when I solve this right-hand side, I get that that is equal to 15.32. So I'm going to rewrite this in exponential form. 10 to the 15.32 equals the energy. And by solving that, we get 10 to that answer. We get that E is equal to 2.09. We're going to round that to the second decimal place, times 10 to the 15th power. So looking at these two answers, that's a big difference between a magnitude 7 earthquake and a magnitude 6 earthquake. Look at the exponent on our scientific notation. This one has an exponent of 15, and this one has an exponent of 13. That's significantly greater, the amount of energy in joules released. Then it says, as a comparison, a 1 megaton nuclear weapon would have an energy release of 4.18 times 10 to the 15th joules, and the eruption of the volcano Krakatoa in 1883 produced an energy release of 2.09 times 10 to the 19th joules. So this is actually this earthquake has the same amount of energy released, a magnitude 7, almost the same amount as a nuclear weapon. I mean, it's to the same power. Now, the value itself, it's about half. But that's pretty intense just for an earthquake. So hopefully you can see that we can use the relationships and the methods that we use to solve just basic equations in these application problems. Thank you.